Hello, everybody. I'm Nicolas Rinaudo, and as is very clear from the title of the talk, I'm here today to talk to you about categorical abstractions, monads and stuff. Not because I find them particularly exciting, but I had never been to Warsaw before. I really wanted to go, and I felt, knowing the Scala community, that talking about monads was probably the best way I had of getting invited. So far, everything is going according to plan, but I have been told by a few people here that my plan was flawed to begin with, because I shouldn't have been trying to go to Warsaw, but to go to Krakow, apparently. So I don't know whether that's true. It's apparently a controversial topic, so I'm going to stay well clear of it. But the problem that I have now is that I have to find something interesting to say about monads and stuff, which is a subject that has been done to death, right? It's not very interesting to begin with, and everybody's been talking about it. So the way I did it, the way I tried to find something, is to look at the way it happened to me when I tried to learn about these abstractions. And usually the way you taught to use them, it goes something like that. You taught about what is a type constructor, and then sometimes under a set of constraints, it can be a functor, and if it follows a few more constraints, then you can have an apply, which can either be an applicative or a FlatMap, and if it's both, then you get a monad. And then people give you examples, such as list, option, either, try, function, and all of them are all of the things. None of them is just a functor. Every single one of them is a monad, which I find extremely frustrating, because what's the point of having all these layers of abstractions if you always only use monad in the end? What's even the point? And it ties into the way I like to learn about things. When I'm trying to learn a new abstraction, I like a new definition, sorry. I like to have examples so that I can have a rough idea of what it is, but I also quite like to have counterexamples so that I have a good idea of what it's not, so that I can shape the boundaries of the thing I'm working with. And back when I was trying to learn these things, such examples did not exist. So I decided to set out and write these things, which is what we're going to do now. We're going to try to talk about data types that are some abstractions, but not other abstractions. So things are things, but not other things. And the way we're going to start is we're going to talk about something that is not a functor as a warm-up. So first, we have to talk about a type constructor really quickly. A type constructor is something that looks like a type, but it's not quite a type because it has a parameter. So typically, option is not a type, but option of int will be a type. So option takes a type as a parameter to create a new type. It's a type constructor. And we want something that is a type constructor, but that is not a functor. So functor, assuming that you have a type constructor called f here, and you have a value of type f of a. And what you want to do is to get to a value of type f of b, and in order to do that, all you have is a function from a to b. Well then, functor is useful because it allows you to use map to lift your function into a function from f of a to f of b. It's quite useful, and the way we're going to do these things, we're going to try to find examples of things that are the thing, so something that is a functor, and then we find a way to break it, because as an engineer, I do like to build things, but I find it a lot more entertaining to actually break them down in interesting ways to see what comes off. So we're going to be breaking all these things for the rest of the talk. And the first example we're going to use here is maybe slightly esoteric as a functor, but we're going to use a function from some x to a, where here x is some concrete type. I don't really care which. It can be an int, it can be a string. It's not important. And a is a type parameter. So the diagram on top here is basically the same as before, only rearranged for function. We still have our f of a, function from x to a. We have a function from a to b, and we want to go from x to b, right? And that's pretty easy, isn't it? You just combine the two arrows. You go from x to a and then from a to b, and you get your function from x to b, right? So pretty straightforward. The reason it works, however, is only because f of a and f compose, right? One ends where the second one begins, so you can put one after the other. So if you want to break it, the best way of breaking it would be to change that. And one way of doing it is to take this x to a and flip the arrow. Because here, there's no way you're going to be able to compose. Whoops, sorry, that went a bit fast. There's no way you're going to be able to compose f of a and f because they start in the same point, go to different positions, they're not composable. So if you can't compose them, you can't implement map. And then you can't have a functor. So you get a data type that is a functor, that is a type constructor, but not a functor. So to make that a little bit concrete, we're going to put names to these x's and these f's. Typically, x, we could say, is Boolean. And in that case, f, a function from A to Boolean, is called a predicate on A. And that is our first counterexample. A predicate is a data type that is a type constructor, but not a functor. What we've learned so far, we've learned that a function, when parameterized on its output type, is a functor, but when it's parameterized on its output type, no, it's the other way around, sorry. Output type is a functor, input type not a functor. And that was the first step of the thing I wanted to show you, but before we go into the rest of the presentation, I need to take a quick break and talk about product types a little bit. In case you're not familiar with the concept of product type, you probably have heard of them under another name, like record or struct, or in Scala, case classes. It's just different types, different values, different types that you stick in the same type, right? So an A and a B, for example. And here, I'm going to use product types that are cleverly called product, because it's not at all confusing. And here, product is composed of a value of type A and a value of type B. And it's going to be important through the rest of the talk because it's going to be the basis for all of the other counterexamples. Now, two interesting things about product types. The first one, the introduction rule. If you have an A and a B, then you can always build an A and B by product introduction. And similarly, if you have an A and B, you can always get an A and a B via product elimination. And this is interesting because these kind of products are always functors, which we're going to look at right now. So say that our f, our type constructor, is an A and an X, where X is, again, a concrete type. Then, this is the same diagram as before. We have a function from A to B, an f of A, and we want an f of B. We know the shape of f of B, right? It's a product type, so it's going to be something that looks like a B and an X. Now, from here, we still have f of A, and we know that we can use product elimination on that, so we get an f of an A and an X. And we have an A and a function from A to B, so we get a B. And now we have a B and an X, which allows us, by product introduction, to get an f of B. So now we have a valid implementation of map for our product type. And so we can say, kind of hand-wavy, but that product like that is a functor. I should be proving the laws as well, talking to you about the laws. I'm not going to do that, mostly because I only have 30 minutes. So we're just going to assume that everything I'm doing is lawful. Right, so what we've learned so far. We've not learned much. We've learned that a binary parametric product type, I'm going to say product from now on, because that's a bit of a mouthful. So a product is a functor. That's all we know so far, but we're going to start adding more information to that. We have already seen an example of something that was a type constructor, but not a functor. And now we want to go something that is a functor, but not an apply. So this part of the diagram, we have something that is a functor, so product, and we want it to not be an apply. Where apply is, to simplify again, characterized by the presence of the map2 function, which is useful when you have an f of A and an f of B, kind of like before, except it was just an f of A. So you have an f of A and an f of B, you want to get to an f of C, and you have a function that takes an A and a B and goes to a C. Well, then you can use map2 to lift that function into an f of A and f of B to f of C, right? And so if we say that our type constructor, our f, is product, then here's our function from an A and a B to a C, and we want to go from an f of A and f of B to an f of C. We know the shape of f of C. It's a product, so it's going to look like a C and an X. And as before, we go to the beginning of a diagram, use product elimination, which gives us an f of A and an f of B. Now, this is going to go a little bit quick, but I'll slow down afterwards. We're going to use product elimination and product introduction twice in a row to get this. Now, we get an X and X, because f of A and f of B both contain an X. So product elimination gives us 2X, product introduction gives us an X and X. Similarly, we get an A and B. And if we have an A and B and a function from A and B to C, well, then we get a C, right? And what we really wish we had at this point is an X. because given a c and an x, then by product introduction, we get an f of c. But we don't have an x. We have an x and x. So we need to somehow be able to take these two x's and combine them into a single one, right? And that choice of name, combine, is of course not at all coincidence. If you're familiar with semigroups, is because what I'm saying really here is that we want x to be a semigroup. So we want to be able, given two x's, to turn it into a single x. And if we have that, well, then everything works out, because then we can call combine to get an x. And if we have a c and an x, then we get an f of c by product introduction. And this is our final diagram, which we are now going to try to break. Now, we've seen that the reason this all worked was because we had combine. So in order for us to break that, we need to make sure that whatever x we pick does not have a semigroup, does not have a combined function, which on the face of it might seem a little bit complicated to achieve, because for any data type, I can give you at least two valid instances of combine, right? Given two x's, I return the first one, or given two x's, I return the second one. So from a structural perspective, it is impossible to build an x that does not admit a semigroup. Semantically, though, we could try to come up with an example in which it wouldn't make sense. So an example that I personally absolutely hate, because it is my life every day and I hate it. Are any of you familiar with Jira? If you're not, I assume you are going to be very soon at some point in your career, and I'm very sorry for what you're about to go through. But in Jira, which is a ticketing system for those of you who don't know, you have tickets that you can associate tags to. So for example, for a given ticket, you could say it's a back-end ticket or a front-end ticket, or you could say it's a bug, or you could say something that needs to be released, to be finished before we release V1. So you have a number of labels that you can associate with a ticket. And I'm, of course, going to use label as an X, because say that you represent these labels as an enumeration label. It doesn't really make sense to prioritize one over the other, right? If you have a ticket that is both front-end and a bug, when you're given a front and a bug, you don't want to turn them into just a front, because you lose information. And similarly, if you just pick the bug, then you lose the fact it's front-end. So you can't really combine them. It's by design a type that is not combinable, that does not have a semigroup. So given that label, we can then go back to our diagram, replace x by label, which means that we cannot implement combine by design. We've specifically crafted label to not be able to be combined. And then if we can't combine it, then if we can't have combined, we cannot call it. If we can't call it, we don't get an x and a c, so we can't get to an f of c by product introduction. And we can't implement map2. And we have a data type that is not an apply. Now we're going to give it a name to make it a little bit more concrete. F here is the product of some value and its label. So we're just going to call it labeled. And that is our example of a data type that is a functor, but not an apply. And we've learned one more piece of information here. We've also learned that product is not an apply if the other member is not a semigroup. And if you're not sure about semigroup, it basically means it doesn't have combine. Right, now further in our diagram, we have something that is an apply, and we do not want it to be an applicative. So that part is the diagram, right? We have an apply, so product, where x is a semigroup, and we want it to not be an applicative. Where applicative is defined by the pure combinator. So sometimes you find yourself in a situation where you have an A, and you need an f of A, for whatever reason. Well, then that's what you use pure for. Pure takes an A and turns it into an f of A. Now, let's take our product as our type constructor and try to see how we could implement pure. So we need to have an A, and we want to go to an f of A. And in order to do that, well, we know the shape of f of A. It's a product. And we have one half of the product. We have an A. We, however, do not have an x. And we can't really pull one out of thin air for any data type x, right? For some data type x, we can. If such data type, if x is such that it has the empty function. Again, not at all a coincidence. Empty is is a combinator on monoid. If you have a combine and empty function, then you have a monoid. So here we're talking about x that has got to be a monoid. And because if it is a monoid, then we have empty, which allows us to both have an x and an a, and then to create to finish implementing our pure implementation. Now, what does this all work? It all works because we have empty. So we need to find a data type that is a semigroup because we want it to be an apply, but that does not have an empty method. So we're going to replace x by something like what I just said, and what I'd like to use as an example for that is weight as a positive int, so a non-zero positive int. Because this has a combined method. You can add two weights together, but you can't have something that has a weight of 0, that has no weight. We're going to pretend here that that does not exist. So if you do that, then it is impossible to implement empty because you really want to return 0, but 0 is not a valid value of type posin, so you can't do that. So you're stuck. You can't implement empty. And if you can't implement empty, you can't use empty. And if you can't use empty, you can't implement pure. And if you can't implement pure, then you don't have an applicative. And as before, we're going to give that a name. It's the association of some value and its weight. So we're going to call that weighted. And weighted is our counterexample, our thing that is an apply but not an applicative. Which is the one more bit of information that we've just learned. A product is not an applicative if the other member, if the x, is not a monoid. Right. So now, we don't actually have that much left to do. We want something that's an apply but not a flat map. So an apply, so we want to have a product with an x that is a semigroup. And then we want it to not be a flat map. Now, flat map is defined by the FlatMap combinator here, which is useful when you have an f of a and you want to get to an f of b. And all you have to go from one to the other is a function of type a to f of b. If you're in that situation and your f is an instance of FlatMap, then you can just take f and lift it through FlatMap to an f of a to f of b. We are now going to try to implement FlatMap for our product of a and x, where it's the same diagram as before, right? We have an f of a and a function from a to f of b, and we want to get to an f of b. We know the shape of f of b, it's a product, so we could replace that. And now, if we start at the beginning, we can use product elimination of an f of a to get an a and an x. If we have an a and an x, if we have an a and a function from a to f of b, then we get an f of b. I had nothing to do with it, Adam. I'm very sorry. Okay, it does not like the abstractions. Let's try to keep going. Where was I? Sorry, that's completely threw me for a loop. Where was I? Right, we get to an f of b, right? Yeah, we get to an f of b. And we want to say at this point that we might be done, right? What we were trying to achieve is to get to an f of b, and we have an f of b. However, the problem here is there's an x there that we're leaving on the side. And this is probably not what we want to do, right? We don't want to forget about data. Now, technically, if you really want to get technical about it, if we leave the x on the side, it means we're violating one of the laws of FlatMap. I'm not going to go into the details. I'm just saying you can't leave some data on the side. Now, if you can't leave data on the side, it probably means that this f of b is an intermediate step to whatever we want to achieve, but is not the final f of b that we want. We probably really have a diagram that looks a bit like that. And now that we have this f of b, well, it's a product, right? So we can use product elimination, which gives us a b and another x. And now we have an x and x, and we know that since we're working on something that is an apply but not a flat map, x must be a semigroup, so we have a combined function, and so we can get to an x. And we have an x and a b, so by product introduction, we get an f of b exactly like we wanted. And that is a valid implementation of FlatMap for our product type. And the problem here is we did not make any special presupposition on x to get from the beginning to the end. So it might feel like it's impossible to actually break this, because there's nothing special about x here. But, well, we can break it. It's a little bit tricky, but I'm quite good at breaking things, so I worked it out. Let's take it one step at a time. Start from b, because you need to get a b to get to the end, right? And the only reason we got a b is because we had an f of b to extract it from. The only reason we had an f of b is because we had a function from A to B and an A. And the only reason we had an A was because we had an f of A, and an f of A contains an A. What if it did not? What if we didn't have an A in f of A, right? In that case, well, we don't have an A, so we can't use the A. If we can't use the A, we can call f on that A. If we can't call f on that A, then we don't blah, blah, blah. The whole thing comes undone. We can't implement FlatMap. So if we remove the A from f, then it is something that is an apply, because X is still a semigroup, but it's not a FlatMap anymore. So that might look a little bit weird. F of A is got an A-type parameter in the types, but not in the values, but it's perfectly valid. It's going to compile, it's fine. It's actually got a name, it's called a phantom type, because it's a little bit spooky, I suppose. Right, so now we need to figure out some X for which that works. And we said that we wanted to be an apply, so X has got to be a semigroup. A semigroup that we already found was positive int. So if we make X into a positive int, then we have an example of a data type that is an apply, but not a flat map. We're going to give it a name. This time, it's not the product of an A and its weight, it's just a weight, so we're going to call it weight. And weight is the counterexample we were looking for. So we've added one bit of information to all we had. Now we know also that the product is not a flat map if it is an apply, but the type parameter is a phantom type. And now we've actually seen all the rules we needed in order to construct the counterexample, because the rest is just going to be more of the same. If we want to find something that is an applicative but not a monad, well, right, we know how to get to applicative. It's got to be a product where the X has a monoid, and we want it to not be a flat map, because a monad is a flat map and an applicative, right? So we want something really that is applicative but not a flat map. And we've seen that in order for something to not be a flat map, we just needed the A to be a phantom type. So what we could do here is take something that is a monad, for example, and make the type parameter phantom. So let's take an example of something that is an applicative and doesn't have a phantom type. So it's got to be a product of A and something that has a monoid. And a monoid I quite like to use is Boolean with false as the empty value and or as a combined value, because it gives us a flag, right? Something is flagged. And if you have two values that are not flagged and you combine them, then you get something that is not flagged. But if either of them is flagged, then the entire thing is going to be flagged. So we're going to use flagged as an example. Flagged contains an A and the corresponding Boolean, the matching Boolean. And of course, we can easily implement pure because we can use false as the empty element. And similarly, we can easily implement flat map because we can use or as a combined element, right? And now, at this point, we know exactly what we have to do. In order to make that not a flat map, we need to make a phantom. Because if you make a phantom, then the entire thing comes undone. You can't implement flat map. And you find yourself with a data type for which you can't implement flat map. And flagged here, well, it's not really flagged, is it? Because it's not the association of a value and its flag. It's just a flag, so we're just going to call it flag. And flag here is a data type that is an applicative, but not a monad, because you can't implement flat map for it. So that's a counterexample we wanted, and we've added something that feels like maybe not exactly new information, right? We've said it's not a monad if it's an applicative with a phantom type, but we've just said it's not a monad if it's an applicative and not a flat map, which is obvious because it has to be a flat map to be a monad. So it's not really new, it's just an example of the thing. And finally, the last bit is going to be something that is a flat map but not a monad, which, again, it's got to be a flat map, but in order not to be a monad, we have to make it not an applicative. So we have to get an example of something that is a flat map, and in order for it not to be a monad, we need X not to be a monoid, right? That's the rules we've seen so far. So we can, again, start from flagged, like before, because we know that flagged is a monad. And to break that, well, we want to replace Boolean by something that is a semigroup, because we want it to be an apply, but that is not a monoid, because we don't want it to be an applicative. And we have seen an example of that, right, before. Something that is semigroup, but not a monoid. We've seen that the weight has a positive int. So if we say that flag is a product of an A and a positive int, then what we can still implement combine is just addition, right? So that works. But on the other hand, we cannot implement pure because there is no value to stick there instead of false. We'd like to put 0, but we can't because 0 is not a valid positive int. So we can't implement pure. If we can't implement pure, we don't have an applicative. And if we don't have an applicative, then we don't have a monad. And so at this point, all that's left to do is to rename flagged because it's a product of an A and its weight. So it's actually something we've seen before. It's weighted, which is an example of something that is, what was it? A flat map, but not a monad. And I believe this is all I wanted to show you. We have reached the point where we've seen all of the counterexample. The last point was a monad that is not a flat. Sorry, product is a monad. Is not a monad if it's a flat map and the other member is not a monoid. Now, to summarize, we've seen, well, all this, right? But to make it a little bit more dense, really, we've seen 3 amusing things, really. The first, well, we've seen that functions, the only counterexample we could find for functors were functions. Now, technically, it means they're actually functors, a special kind of functors, they're contravariant functors, and I believe that's the only counterexample for functors. But we've seen that function, if you flip the arrow, then was not a functor. We have seen that apply and applicative had a deep connection with semigroup and monoids. Now, that's not exactly new information. If you read McBride's paper on applicative functors, it's there, front and center of the paper. It's a large chunk of the paper, this connection. But even when I read the paper, it didn't really click. And seeing it as part of this search for a counterexample really made it feel a lot more concrete and understandable for me. And finally, we have seen that monads, this one is a bit weird, right? A monad needs a value in order to work. So it doesn't, on the face of it, seem to really make sense. But I think it's just a complicated way of saying that monads are about chain computation, and you need a value to thread through the computation, right? So if you don't have the value, you can't thread it through the computation, so you can't chain computations. Which may be a bit weird way of expressing it, but I think still probably a better way than saying it's burrito or whatever. Now, I don't know if any of this information was new or useful to any of you. I hope it was entertaining. At least it was for me. It's quite fun to write this presentation and break these things to get interesting things out of them. And if you have any question, now is a good time to ask them.
All right, do we have questions? Be bold, ask.
What do you mean, we will answer?
Please, could you show again an example of type which is a flat map, but not a monad? Does any useful type like this exist?
Well, I mean, I've shown a useful type for, well, useful, for a given value of useful. I think that was the one, right? It's a flat map, but not a monad. Yeah, that's the one. Weighted. It's a flat map, but not a monad, because you don't have pure. So if you want to associate some value, and that's really bright, if you want to associate some value with something that is not a monoid, such as a positive int, then that is a flat map, but it's not a monad, because you can't implement pure for it, so it's not an applicative, so it's not a monad. So that's an example. Whether it's useful is up for debate. I have had to use it in my code. You might not have, so it might not be useful to you. It was useful to me, at least to stick in that presentation.
Oh, it looks great. Thanks.
You're welcome. I'm not entirely sure why they're clapping, but I like it. Keep doing it.
It's just fun, you know, when they clap.
I think it's because it's the end of the day and it's about to be the party.
You think so? I don't think so.
I think there's another question. Yeah. Yes, hi.
Yeah, hi. Thank you for the great presentation. Yeah, that's too bright. I just want to have like one question, because you said that we should believe that this is lawful. Well, I would like to question if we chose like a dummy implementation of combine for weighted, would it be lawful? Like if I just, you know,
it depends what you mean by lawful. It's a very good question. It is a very good question. So the question is, for example, for weighted, we could provide an implementation of combine, right? We get two weights and we pick the first one. For example, hang on, no, it was pure the problem. So we could say, But combine was for, it wasn't for weighted, combine was for labeled, yeah, thank you, perfect. So we could just choose one label at random, provided we always choose the same one, so always the left one or always the right one. It would be legal if you strictly follow the laws, but it also means you haven't followed the specifications, because the specifications were you cannot combine label. So if your solution to a problem where you cannot combine labels is to combine labels, maybe you're not on the right track. I would argue that maybe your manager might have words with you afterwards.